Swayam Prabha. Digital India. Educated India.
Our next topic is functions. So this is something we have already been using implicitly. So let me start with reminding you of one example we used. So we talked about predicates as assigning, for elements in a domain, for each element, a truth value, true or false, right? So that is what a predicate is. So this is a special case of a function where true and false, the set containing these two elements, forms the codomain. Okay? So those are the values that get assigned to each element in the domain. A function could be more general, where the codomain could be an arbitrary set, right? Doesn't have to have just two elements. Okay? And in this case, we denote the function like this. So here A is the domain and B is the codomain. So we say that a function maps each element in the domain to an element in the codomain. So that's basically a table like this. You could imagine for every element in the domain, we write an element in the codomain opposite that. So to specify a function fully, we had to tell, we had to say what the domain is, what the codomain is, and this mapping, something like this table. Okay. So here is an example. So I took the predicate we had, which was in the previous slide, the example saying, Alice likes herself, Alice doesn't like Jabberwock, and so forth. And now I'm generalizing it instead of just assigning true or false. Here is a function which assigns it a value. So for each pair here, it assigns a value in the range 0 to 5. So you could think of this as the extent of liking in a scale of 0 to 5. Okay, so Alice likes herself very much. So the function maps the pair Alice, Alice to 5, but she doesn't like Jabberwock much, so it assigns it 1. And say the Jabberwock likes itself a lot, but not all that much, so we assign it a value 4, and so forth. Okay, so let's use this table to say what exactly a function should look like. So every element in the domain, so in this case the domain is the cross product of the characters in Alice in Wonderland with itself. So AIW cross AIW, where AIW is the set Alice, Jabberwock, and Flamingo. And so all 9 elements in that set, in that domain appears here, and everything gets assigned a value. So no empty slot. And also every slot here has exactly 1 value. So you cannot assign 2 values to the same element in the domain. If you look at which values in the codomain got used in this table, we do not guarantee that all these 0 to 5 would get used. To be a valid function, it's okay for it to use only a strict subset of the elements in the codomain. So in this case, only 0, 1, 4, and 5 are getting used by the function. So that's this set of values which did get used by the function, 0, 1, 4, 5 in this case, would be called the image of the function. So formally it's a set of all values in the codomain such that there is some element in the domain which is mapped to that value in the codomain. And so again, this is familiar notation of f of x denotes the value that is assigned to x by the function f. Okay? So again, image of f is a set of all y in the codomain such that there is some element in the domain which is mapped to y by the function. And another useful visualization of a function is using this kind of a diagram where every element in the domain is listed here, every element in the codomain is listed here, and you put an arrow from the element in the domain to an element in the codomain that it is mapped to by the function. And this way you can quickly see, for instance, that the image is only 0, 1, 4, 5, 2 and 3 doesn't have anything mapped into it. Okay. Now that's we describe it in English. We saw some visualizations, but if we had to formally define what a function is using things we already talked about, one way to do it is think of the function as a relation. Okay. So before that, what we just now did is we defined a function, or we saw that a function is a generalization of a predicate. And a predicate was essentially a way to represent a relation. Right? So a function is a generalization of a relation. Another way to say that is a relation is a special case of a function, or you could view a relation as a special case of a function, namely a function which is a predicate. Conversely, you could also think of a function as a special case of a relation. Okay, so that's what I'm going to show you now. So you could think of the function, and there's a formal way you would define a function, as a relation. It's a heterogeneous relation relating elements in the domain to elements in the codomain. So technically it's just a set of pairs x comma y, where y is the value that you want to assign to x, so f of x, right? So for every element in the domain, there will be a pair of the form x comma fx in the relation that captures the function. So since it's a relation, you could use the representations we have been using for relations. So since it's a heterogeneous relation, the domain and codomain could be different sets. I've shown two colors for the nodes, but they could be the same set. They could be overlapping sets. But for clarity here, I've shown them as two disjoint sets, and you have arrows going from elements in the domain to elements in the codomain. But it's not just any arbitrary relation. It has to have the property that every element in the domain has exactly one outgoing arrow. So it's related to exactly one y in the codomain. So there's a unique y such that x comma y is in the relation. Right? So this is a special kind of relation, and these relations are functions. So functions can be thought of as a special kind of relation, just like relations could be thought of as a special kind of functions. Okay, and when you think of function as a relation, you could represent it using a matrix, which is what we've been doing for relations. So in this case, the convention is that you would write the domain as columns and the range as or the codomain as the rows. Like, when we were drawing relations earlier, we actually used the opposite convention. The first coordinate was represented in the rows, and the second coordinate in the columns. Here, the convention would be to do it the other way. This convention would match what how you would plot a function, right? You think of, for every value x, you plot in the y-axis its function value. Okay, so here Alice comma Alice is mapped to 5, Jabberwock comma Jabberwock is mapped to 4, and so forth. Okay, so there's the function we had in the previous slide. And the special property is that, so it's not that you can take any matrix and that would correspond to a function. You should have, for every column, there should be exactly one element that is one cell that is switched on, for which the entry in the matrix is true. So exactly one, right? So you cannot have 0, you cannot have 2, 3, or more. You should have exactly one element per column. Okay, so this visualization works when your domain and codomain are finite sets, otherwise it doesn't quite work, but you could still informally use this kind of representation. Often we deal with functions which are numbers, so the inputs and outputs of the function could be numbers. So in these cases, when the domain and codomain are integers, real numbers, or even they are totally ordered, they need not be numbers. In these cases, it might be useful to plot the function to get a sense of what the function is doing. For instance, here is a function defined from, say, natural numbers to natural numbers. It happens to be the identity function, and this is a plot for the function. So this is just our metrics for every x every input x in the x-axis. I have plotted f of x. I have marked that as true, and all the other rows as false. So, but now this looks like a graph that you would be familiar with for plotting functions. And of course, the function in this case has an infinite domain and codomain, but it's still useful to see the function plotted like this for a subset of the domain and codomain. Here's another example: f of x equal to x squared. Again, take the domain as integers, and then and the codomain also as integers. And this is what the plot looks like. You can recognize the familiar parabola here. Note that for every integer x, there is exactly one column that is switched on. And here's another function, f of x equal to 5x. So it's again looks like a line, but with a higher slope. And you would see some, in both these functions, you would see an apparent gap between different points, but there are actually outputs for consecutive inputs. Here's another function, f of x equal to the floor of x divided by 5. So even if x is not a multiple of 5, you need to assign it some value. So that's why we are taking, and we are setting the codomain to be integers, domain and codomain to be integers. So that's why we're taking the floor here, so that every element here does have an output. And here again, visually you can see a line with a smaller slope. So that is the function f(x) equal to x by 5, in this case the floor of x by 5. So one last thing I wanted to include in this lecture is an operation you can do on functions. So given two functions f and g, you can define the composition written as g of f, or you would read it as g of f. So it's a function that it simply takes an input x, applies f to it first, and then whatever output f gives, you apply g to it, right? So it's g of f of x. So it maps elements in the domain of f, to the elements that g output. So these are elements in the codomains of g. Okay, so here is an example. So let's pick our f, which is assigning numbers in the range 0 to 5 for pairs of elements from Alice in Wonderland. So for instance, assigns 5 to Alice, Alice, 4 to Jabberwock, Jabberwock. And now I define a new function which takes these numbers in the range 0 to 5 as its input and assigns them labels, so high, medium, or low. And now I can talk about the composed function g of f of x, such that it takes, say, Alice, Alice, and maps it first to 5 and then maps 5 to high. So g of f of Alice, Alice is simply high. Okay, and similarly, I can, for all the 9 elements in the domain of f, assign some value in the codomain of g by following these arrows. So, this is uniquely defined. F of x, there is a single value, and then you apply g to it, you get a single value. You'll always get a value. Okay, so that is composition of two functions. So sometimes this convention of whether you write it as g of f or f of g can be a little variable across different sources. For us, you should read this as g of f. So this is easy to remember, g of f of x. So the input x is applied at the right end of this notation here. So f is applied to x, and whatever comes out, you apply g to it, and that's the output. One thing to be a little careful about, though, is that if you're drawing this kind of graph, the arrows, then it works in the other direction. So the inputs are on the left and the function's outputs are on the right. So when you want to find g of f of x of Alice, first you follow f and then you follow the g arrow to get to where g of f of x maps it. Okay, so that's just something to be careful about. If you're confused, remember you can read this as g of f of x. Okay, so technically g of f of x is can be defined whenever g assigns a value to every possible output that f gives you. So even if g was defined only for the domain, for g's domain 0, 1, and 4, 5, you could have still defined g of f of x. So technically, whenever you have a function g whose domain includes all of the image of f, you can define g of f of x. However, typically you would define g of f of x with where g's domain is the entire codomain of f rather than just the image of f. G could have more, G could have something larger than the codomain of f, but often this is the situation you would find yourself in. F will be defined with a codomain which is the same as G's domain, so that when you define G of f, you don't have to worry about what exactly the image of f is. And as I already mentioned, this is a function that maps elements in f to elements in the domain of f. So that's here all the way to elements in the domain of G. And the image of this composed function, so in this case, g of f, the image is just a set high-low, even though g's own image is high, medium, and low, the entire set here. So all we can say is that the image of g of f is a subset of image of g. It need not be all of the image of g. That depends on how the output from f, what all elements they hit in the domain of G. Okay, so that's all for now. We'll continue with different kinds of functions in the next video. Now we will discuss different kinds of functions, mainly one-to-one functions, onto functions, and bijections. So here is a quick summary of what these different types of functions are using the metric representation we had. Just to quickly visually understand what these different types of functions are. So recall the way we represent a function as a matrix here. Every column corresponds to an element in the domain, and every row is an element in the codomain, and we switch on a particular entry for every column. So just being a function means every column has exactly one cell that is switched on. Now you can think of onto functions as those functions where every row has at least one cell switched on. So remember, the function didn't say anything about how many cells should be switched on for every row. It said every column has exactly one cell switched on. An onto function is one in which every row should have at least one cell switched on. And the one-to-one function, on the other hand, says every row can have at most one cell switched on. And a bijection says every row should have exactly one cell switched on. Okay, so that's in a nutshell the three different kinds of functions we will talk about, but let me expand on that. So first, surjective functions, or onto functions. So every row has at least one cell switched on. So in this examples here, these two functions, fx equal to x and fx equal to 4, fx divided by 5, they do satisfy that property. Whereas on the other hand, here, so there are several rows that you would see will not have any cells switched on. Even though you might be defining this function for all the integers and then showing only a part of the whole domain, you can see that there is nothing that's going to be switched on in some row here. Okay, and similarly, fx equal to x squared, there are several numbers which are not perfect squares. And here it is that there are several numbers which are not multiples of 5. So these two are not onto functions, whereas these two examples are onto functions. Now, you could take any function and recast it as an equivalent function simply by changing the codomain, simply by redefining the codomain only to include those numbers which are in the image of the function. Okay. So for instance, if I define my function fx equal to 5x as a function from integers, from the set of all integers, to the set of multiples of 5, then it would become an onto function. Okay? So an onto function essentially says the image of f is the same as the codomain of f, and you can syntactically change the codomain to equal the image for any function. Of course, you may not want to do that because you don't, it may not be easy to see what the image is. You might still want to define the function before knowing what its image is. So not every function you define would be onto, or alternately, because the image is just a difficult set to describe, so you would not define it as an onto function. Okay. All right. So that's onto functions. By the way, the formal definition of an onto function would be that a function f from a to b is onto it for every y in the codomain. There exists an element in the domain such that f of x equals y. Okay. The next type of functions we talked about is injective functions or one-to-one functions. So here, every row has at most one cell switched on. So in these examples here, this is clearly not a one-to-one function because there are rows which have multiple cells switched on, 5 cells switched on. So this is not a one-to-one function. This almost looks like a one-to-one function, but here again there are cells which have 2 cells switched on. That is enough to make it not a one-to-one function. Okay. On the other hand, these two functions are one-to-one. Every cell has at most one cell switched on, though notice that there are several rows which do not have any cells switched on. Right? So every row has at least one cell switched on. There may be rows which do not have any cells switched on. You do not want a row which has 2 cells switched on. Okay, so that's a one-to-one function. So this is a one-to-one function. This also is a one-to-one function. Now the domain matters. Just like you could manipulate the image and make any function or onto function, you could manipulate the domain and make any function a one-to-one function. However, you will be losing some information about the function. You will only be talking about a part of the function. So here, for example, I could take the function fx equal to x squared, and if I restrict myself to the domain of positive integers, so only things to the right of the 0, then it is a one-to-one function. Okay. On the other hand, if I allow positive and negative integers, then it's not a one-to-one function because x squared is equal to minus x squared. A class of useful examples for one-to-one functions when you are talking about functions from a numerical domain to a numerical codomain are strictly increasing functions or strictly decreasing functions. So if, for instance, I restrict, so this is a strictly increasing function. This is not a strictly increasing function. So the definition of a strictly increasing function is that if x1 is greater than x2, then f of x1 should be greater than f of x2. So here it is the case that if x1 is greater than x2, I can guarantee that f of x1 is greater than or equal to f of x2, but that is not a strictly increasing function. This one is an example of a strictly increasing function, so is this. So is this if I restrict myself to just the positive integers. Those would all be one-to-one functions. And it's the same thing for strictly decreasing functions. For instance, if I restrict myself to the negative integers, this would be a strictly decreasing function, and that would also be one-to-one. Of course, these are not the only examples of one-to-one functions. These just happen to be two interesting examples of one-to-one functions. Now, and okay, here is another way to write what a one-to-one function is. Actually, here is a more direct way we would write what a one-to-one function is. For every element in the image, their x is a unique. So the symbol here you should read as their x is a unique x in the domain such that f of x equal to y. So this notice is written for y in the image of f. There could be y in the codomain of f which are not in the image of f. So those do not have any x mapping to them. We are okay with that. But whenever there is some x mapping to y, we want it to be unique. We don't want two x's to map to y. Okay? Another way to say that is this. If you take any pair x prime in the domain, and if it so happens that f of x equals f of x prime, then it must be the case that x is equal to x prime, right? So the only way f of x can be equal to f of x prime is if x and x prime are equal. So if x and x prime are distinct, so they are different columns, then they map to different images. So they will not have the same row switched on for them. Okay, so that is what an injective function is. An important property of an injective function is that it is invertible. So what is an invertible function? Say a function is invertible, function f is invertible, if there exists some other function g, such that when I compose g with f, so g of f should be the identity map from the domain of f to itself. Okay, so the identity map just maps elements to themselves. So another way to say that is, if I gave you f of x, if I took an arbitrary x and computed f of x and gave it to you, you will be able to tell me what x is. Looking at f of x, you will be able to tell me what x is, because you can apply this function g to whatever I gave you, and that will give you that x. Okay, so you can recover x from f of x, or another way to say that is f is not a lossy function. It doesn't lose any information about its input. So that's what an injective function is. Okay, and sorry, that's what an invertible function is. And I claim that one-to-one functions are invertible. Okay, so why is this? Suppose I give you a one-to-one function. I need to now demonstrate a function g such that g composed with f is the identity function. So let's say this is my one-to-one function, right? So here distinct elements in the domain map to distinct elements in the codomain. There is no element in the codomain to which two different images, two different elements in the domain map. Okay, so this is an example of an injective function. Let's see why it is invertible. To show that it's invertible, I need to define a new function g, and I didn't specify here explicitly what the domain and codomain of g are, but they are going to be just the reverse of what our f had, right? So domain of G will be the codomain of F, so that we can do the composition. And since the compose function should be the identity function going from the domain of F to the domain of F, it better be the case that codomain of G is the domain of F. Right? So this, if F is from A to B, then G is from B to A. Okay, so I'm going to define this function G from B to A as follows. So first I'll look among, so I need to define G of Y for every Y in B. Okay? So I consider two cases. So Y which are in the image of F. So in here the image of F are these three elements, 0, 1, 1, 1 and 1, 0. So if Y is in the image of F, well, I know that there exists a unique value, right? There exists a unique x such that f of x equal to y. So this 0, 1 has a unique x 1 such that f of 1 is 0, 1. There is not, f of 2 or f of 3 are not going to map to this value, right? So for those, any such element in B, which is also an element in the image of F, I'm just going to find what is the element in A that is mapped to it by F. So in this case it is 1, and I will say G will map this element to that. Okay, so G mapped 0, 1 to 1, G mapped 1, 1, in this case to 3, because 3 is the unique element in A that is mapped into 1, 1. So G will map 1, 1 to 3, and it will map 1, 0 to 2. Okay, so but it's still not a fully defined function. To be a function, I need to define what my G is for every value in B. So for the other values in B, I'll just map them arbitrarily. Okay, so in this case, there's a dotted arrow says that I don't really care where it maps to. I'm just going to map 0, 0 to 1, because to be a function, I need the 0, 0 to be mapped somewhere. So I just mapped it to some arbitrary element in B. Okay, so that's a well-defined function now. And I'm claiming that this function, when composed with F, gives you the identity function. Okay, identity function in A. It maps elements in A to elements in A. So why is that the case? Well, you take any element in A. What is G of f of x? So it equals G of so x is element in A. G of, say f of x is y, so it is G of y. What is G of y? The way we define G of y, it's going to be equal to x. If f of x is equal to y, then G of y is going to be equal to x. So G of f of x will be x. Okay. So for every element in A, G of f of x will be x. For, that's it. That's all I need to worry about. This element that is not part of the image of f doesn't even come into the picture when I'm computing G of f of x, because I'm computing G of f of x for some x in the domain A, and it will never try to access this mapping. Okay, so here is another example. So in terms of how the graph looks, so this is my function. This is a one-to-one function. F of x equal to 5 times x. Let's come up with an inverse for this, following this little proof I have here. So first it says, okay, for every element in x, I have to map with, so I'm defining my G, right? So for every element y, which is elements which are also integers, so elements along this axis, which I've drawn longer here, right? So the vertical axis here, those elements are the ones in the horizontal axis here, and the say you take the point 5 here, right? So 5, f of 1 is equal to 5, so G of 5 will be equal to 1, and G of 10 will be equal to 2, and so forth. Okay, so this so far is the first step here. That does not completely define my function. To finish defining my function, I arbitrarily fill in the remaining values for G. Okay, so there's one way to do it. There are, of course, other ways to do it. So the inverse function need not be unique, but there is some function g such that g of f is the identity function. Okay, so injective functions are exactly the same as invertible functions. The g that you obtained in this way by itself need not be invertible. It's, well, for many values it is invertible, but for this arbitrary value that you picked for mapping, if I told you g of y equals 0 in this example, you have no idea what y is. There are several y's that map to 0. So g need not be invertible, but f is invertible. That's the definition of being invertible. Now, it goes a little further. It's not just that, so what I showed you actually just now is just that if you give me a one-to-one function, it is invertible. But actually it goes in the other direction also. If you give me an invertible function, it has to be one-to-one. Okay? So suppose you give me an invertible function. So what happens if it were not one-to-one? And it means that there are two elements that get mapped to the same y, two elements x and x prime that are getting mapped to the same y. And now if you're asked to invert this y, you will be in trouble. You don't know whether to invert it to x or x prime. Okay, so that's the argument. Here is an argument without using contradiction. So I'm going to just define g. So if you give me f, which is invertible, I'm just going to ask you, give me the g such that g of f is the identity. So you give me this g going from b to a such that g of f is identity. And now I'll just directly prove the condition we wrote for what it means to be a one-to-one function. So take any x1, x2, and I want to prove that if f of x1 equal to f of x2, then x1 equal to x2, right? So what do I do? So if f of x1 equal to f of x2, then I can apply g to both sides. Since these are the same values, if I apply the function to both sides, the equality is preserved, so, right? So g of f of x1 equals g of f of x2. But g is the identity function, so g of f of x is x. So this now reads as x1 equals x2. And that is the proof, that's the statement I wanted to prove, that for any two elements in the domain, if f of x1 equal to f of x2, then x1 equal to x2. Okay, so that completes the proof that invertible functions and injective functions are the same thing. Now I want to talk a little bit about bijections. So these are one way to define them. Was not quite how we defined, we said these are functions for which in our matrix representation every row has exactly one cell switched on. That's the same as saying it has at least one cell switched on and it has at most one cell switched on. That is to say, it is on to and it is one to one. Okay. So that is what a bijection is. It's a function that is both an on-to function and a one-to-one function. Okay, that is, every row has exactly one cell switched on, and of course every column has exactly one cell switched on because it's a function. Right? So a bijective function in a bijective function, every row and every column has exactly one cell switched on. Another way to say that is that every element in the codomain has exactly one preimage. So preimage is a y is an x such that f of x equal to y. So preimage of y is an x such that f of x equal to y. In onto functions, every y has at least one preimage. One-to-one functions, it has at most one preimage. And in bijections, every element in the codomain has exactly one preimage. Okay. And if it's a one-to-one function, it has a well-defined inverse. We just saw, there's a function f inverse, such that f inverse of f is an identity map in A, right? But if you look at the description here, the domain and codomain are treated symmetrically. So if it's a bijection, then you could flip the domain and codomain, and you will get another, so the transpose of this matrix, as it were. You'll get another matrix which corresponds to another bijective function from B to A. Okay, and that function is actually the inverse of f. So if you look as an example here, here is a bijective function mapping 1, 2, 3 to these three things, and its inverse is simply obtained by taking the transpose of the matrix, or in other words, flipping the arrows in this diagram, taking this as the domain and this as the codomain. Okay? So these are all descriptions of the same operations, and that is the inverse operation. So if I composed, if I did f inverse composed with f, so first I do f, so I go from say 1 to 0, 1, and then I do f inverse, so I go from 0, 1 to 1. So in the composed function, I'll go, I go from 1 back to 1, or go from 2 back to 2, right? And similarly, if I did f composed with f inverse, f of f inverse, so then first I will do f inverse, and then I will do f, and I will get back to the same place I started from. So f of f inverse and f inverse of f are both identity functions. They are both, invertible functions. They are both bijections. And when you have a bijection, the inverse is unique. So first of all, this shows this is an inverse. We know one-to-one functions already have an inverse. And there's an inverse for the bijective function. But this is the unique inverse, because if you think about our proof, we said for elements in the image, there is a particular way in which we inverted the edges. And for the other, we didn't have any choice there. We had to invert those edges. And for the other elements, we were mapping them arbitrarily, but there are no other elements outside of the image here. Right? Every element in the codomain is in the image because it's an onto function. Right? So this f inverse is unique. And since f inverse itself is a bijection, the inverse of f inverse is also unique, and that is equal to f. Okay? Since f is an inverse of f inverse. All right, so you should think through that that a bijection has a unique inverse, and that inverse itself is a bijection. Now, the definitions of these functions work for domains and codomains which could be infinite, but it becomes a little simpler to visualize or think of when these domains and codomains are finite, and then you can actually talk about the sizes of the domains and codomains. So suppose f is a function from a finite domain to a finite codomain. So here is one thing you can see that if it's every element in A is mapped to some element in the image. Right? So the total number of elements that you can reach as f of x is as many as the number of x's you have. That's the size of A is an upper bound on the size of all the elements of the form f of x, where x is in A. Okay? So that is to say, the size of the image is at most the size of the domain. When would equality hold? Equality holds if every element in the domain counts towards a different element in the image. Okay? So that is a one-to-one function. If two elements in the image, two elements in the domain map to the same element in the image, then the total size of the image is going to be strictly smaller than the size of A. So the equality holds if and only if the function is 1 to 1. And another simple observation is that the image is a subset of the codomain, so clearly the size of the image is at most the size of the codomain. And what does it mean for this to be an equality? Well, it means the entire image, the entire codomain has to be equal to the image. There is no element left out of the codomain that is not in the image. So image of f is the same as the codomain of f, and that is to say f is onto, right? So the equality holds if and only if f is onto, but there's always this simple inequality, okay? So, these two things would be evident, but of course these make sense only when the sets A and B are finite. Otherwise, the size of these sets are not well defined. They could both be infinite, and then you cannot say things like equality holds only if f is onto or f is onto. Okay? We will actually later talk about infinite domains and codomains. Okay, so here's a couple of consequences of this simple observations. So if f is onto, right, then image of f is equal to the size of b. So this one just says size of b is less than or equal to size of a, right? So if f is onto, then size of b is less than or equal to size of a, or in other words, the domain is at least as large as the codomain. Otherwise, you cannot cover every element in the codomain. You need at least as many elements in the domain as you have in the codomain, so that you can, cover or account for every element in the codomain. On the other hand, if f is 1 to 1, then the reverse inequality holds, and here again, if f is 1 to 1, then the image and the size of the image is exactly the size of the domain, right? And since we also have that the size of the image is less than or equal to b, we have that the size of the domain is less than or equal to b. Okay, so all this is saying is that if f is 1 to 1, then the domain, there's an image of the domain that is as big as the domain itself, and that thing is sitting inside the set B. So set B has to be at least as large as to accommodate this image of A, which is as big as A. Right? So B has to be large enough. B has to be large, at least as large as the size of A. We have actually already implicitly used this particular statement. If you look at the contrapositive of the statement here, it says if A is strictly greater than B, size of A is strictly greater than size of B, then F cannot be 1 to 1, right? So if size of A is greater than size of B, then F cannot be 1 to 1, and this is the pigeonhole principle. So you could think of mapping pigeons into pigeonholes. A is the domain, the set of all pigeons, and B is the set of all pigeonholes. And the mapping, the function f, is saying, each pigeon sits in this particular hole. So every pigeon has been assigned a particular pigeonhole. That assignment is a function f, and that function cannot be 1 to 1. So it will assign 2 pigeons to the same hole, at least 2 pigeons to the same hole. Okay, and if you put these two things together, f is onto and f is 1 to 1, that is to say f is a bijection. So if f is a bijection, it's onto and 1 to 1, and in that case, both these things hold, A less than equal to B and A less than equal to B. Therefore, size of A equals size of B. And in fact, if in this case, if size of A equals size of B, there are a bunch of things, all these different things we talked about, onto, 1 to 1 bijection, they all mean the same thing. They all mean that it's a bijection. So if the sets, the domains and codomain, the domain and codomain of a function are the same size, the finite domain and codomain are the same size, Then if I tell you it has to be on 2, then it has to be a bijection. It has to be also 1 to 1. And I'll leave it as an exercise for you to think through. It follows easily from the conditions above by comparing with the image of F. Okay, and finally I want to talk about how these different types of functions behave under composition. So very quickly, this is what composition looks like, and typically we, all you technically really need for a composition to be defined is that the image of F is contained in the domain of G, but typically we would take function G to be defined, the domain to be, the entire codomain of F. So let's stick to that for now. So suppose domain of G is the codomain of F, and the composition is well defined. Then, of course, as I said, for the composition to be well defined, you don't need this property, but this is a typical thing you would take, and if this property is given, then the composition is well defined. Okay, so first observation is that composition respects on-to-ness in some sense. Okay, so what do I mean by that? So if F and G are both onto, then their composition G of F is also onto. And so here is an illustration. So you can of course turn all this into proofs. I'll just show the pictures, which is probably more useful than writing down a proof. So if so, here is an example of an F that is onto, right? So every element alpha, beta, gamma, delta here is covered by, so they all have some arrow coming into them. And same here in G 1, 2, 3, they all have arrows coming into them. What does G of F look like? So that's a mapping that follows a pair of arrows to get to here, right? Now, and again, this codomain could be different from the one here, even though they are the same color in my example. They're clearly different sets. I'm claiming that this composed function will have to be onto. Why? To be onto, you just go and check if every element here can be reached starting from some element here. So we know that since G is onto, every element here can be reached from some element in G, and since F is onto, that element in G can be reached from some element in the domain of F. So every element here can be reached from some element in the domain of F when you apply G of F. Okay, so that's why this G of F is an onto function. It's not an if and only if condition though. So suppose I added to the domain of, to the codomain of F and domain of G, is one more element, epsilon. And to keep G a function, I said, okay, epsilon, G of epsilon is 3. Then suddenly, F is not on 2 anymore. Okay? F is not on 2. Thankfully, it did not affect G of F. This element didn't matter. But it shows you that, even if I tell you that G of F is on 2, I cannot say F and G both have to be on 2. So here, what I said here is that if F and G are both on 2, then G of F is on 2. The converse doesn't hold. However, what I can say is that at least G has to be on. Because remember, the way I found the pre-image for every element here is by taking a step back in G to some pre-image in G, and then I use on to property of F to get back to something here. But at the very least, even if F is not on 2, I need that if G were not onto, if this element, say 2, was not reachable from anything in G, then it will never be reachable from in G of F either, right? So the image of G of F is a subset of the image of G, no matter what F is. So if image of g of f has to be equal to the codomain of g of f, which is a codomain of g, then it better be the case that image of g is at least equal to the codomain of g. So I can I can say that if g of f is onto, then g must be onto. Again, that's not a sufficient condition. So there's a necessary condition. F and g both being onto is a sufficient condition. Neither is a necessary and sufficient condition. Okay, now let's move on to one-to-one. So to talk about one-to-one, I just increase the size of the domain of the codomain of f and the codomain of g. Added a few more elements so that now f is one-to-one in this example, and g is also one-to-one. There were multiple, say earlier 2 and 3 were mapping to a single element. I gave a new image for 3. So 3 is mapping to something else. Similarly, I adjusted the mapping here so that this becomes one-to-one. And now if f and g are both one-to-one, I claim that g of f is one-to-one as well. So why is that? If two elements were to map to the same element here, so I take two elements here, two distinct elements. Since f is one-to-one, I know that they will map to distinct elements here. And since they are distinct elements and g is one-to-one, I know that they will be mapped to distinct elements here, right? So that's why g of f will be one-to-one if f and g are both one-to-one. Again, it's not a necessary and sufficient condition. It's a sufficient condition, but it's not a necessary condition, because here is an example where the function that I have is still the same. G of f, the composed function, is still the same. I just changed the epsilon, g of epsilon a little bit here, but g of epsilon really didn't matter in the function g of f, right? But the way I changed g of epsilon, g is no longer one-to-one. Okay, so g is no longer one-to-one, even though g of f is one-to-one. So I cannot say that if g of f is one-to-one, both f and g are two. However, again, I can say something about f. I can say that f has to be one-to-one. If f were not one-to-one, say 2 and 3 both map to beta, then doesn't matter what g is, g of 2 and g of 3 will be the same value. So if f had a collision, so to speak, if f mapped two elements to the same value here, then g of f will keep them mapped to the same value. So g of f will not be one-to-one. So for g of f to be one-to-one, it's necessary that f is one-to-one, and it is sufficient that f and g are both one-to-one. But again, these two conditions, one of them is a necessary condition and the other one is a sufficient condition, but we are not giving any necessary and sufficient condition for g of f to be one-to-one. Okay, and finally, since a bijection is simply a function that's both onto and one-to-one, composition will respect both these properties of a bijection, right? The one-to-one-ness and the onto-ness. So if f and g are both bijections, then they are both onto, so therefore the composed function is onto, and they are both one-to-one, so the composed function is one-to-one. So the composed function is a bijection. Okay, it's both onto and one-to-one. And I can just infer a necessary condition from the necessary conditions here. I can say that okay, if g of f is a bijection, then there is a necessary condition of f that f is one-to-one, and there is a necessary condition on g that g is onto. But again, as before, this is not sufficient, and also it is not necessary that f and g are both bijections for g of f to be bijection. Okay. As one last comment, if you change this requirement that we had here, things will look slightly different. And I would leave it as an exercise for you to think it through. What happens if I allowed the domain to be actually a superset of the codomain of F, right? And it would still, the composition will still be well defined, but which among these properties, these statements will we need to change? And what if I took the domain of G to be smaller and I made it actually equal to the image of F? Okay. And what if I also cut down the codomain of F to just to be the image of F? Again, in these cases, these statements would slightly change, and I would leave it as an exercise for you to figure out what happens in those settings. Okay, so I'll leave you with those exercises.